Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 25, part 1 on the topic cold storage design for negative temperature applications. In lecture number 23 and 24, that is the previous two lectures, I have designed cold storage for storing two different type of products. One is potato. In the first design, we designed the cold room for storing potatoes, and in the second one for storing mixed vegetables. Before designing the cold storage for negative temperature applications, so let me give a very brief insight about the temperature range. Normally, when we say the positive temperature application, it's from about say 0 to less than 10 degrees centigrade. Most of the positive temperature application storages are in the temperature range from 2 or 3 degrees centigrade to up to 5 or 6 degrees centigrade. So here, when it comes to the cold room, normally the products are stored the range from minus 20 to minus 30 or minus 20 to minus 25 degrees centigrade. The frozen food such as fish, meat, chicken, etc., all these products are used in the negative temperature. Before designing the cold storage, so there is one slight difference when it comes to the product load. In the positive temperature, the product load is the summation of Q1, Q2, Q3 and Q4. Here also it is Q1, Q2, Q3, Q4. In the positive temperature application, there is a respiration load. So Q4 is the respiration load. So here Q4 is not the respiration load, and the Q4 is the like the sensible heat below freezing. In positive temperature application, Q3 is sensible heat below freezing, whereas the same thing it is in Q4. Then what is the additional heat load that has been added here? So here Q1 refers to the sensible heat due to pre-cooling. Sensible heat due to pre-cooling. That is cooling from ambient to a lower temperature. However, this lower temperature will be above freezing. So MCP T1 minus T2. T1 is the initial temperature of the product and T3 is the final temperature of the product. There is one more temperature which is there in the negative temperature application, temperature of the product after pre-cooling. So in positive temperature applications, we have got T1, T2 and TF. Here we have got T1, T2, T3 and TF. 4 temperatures are there. So based on these 4 temperatures, 4 heat loads, of course, 3 heat loads and 1 is latent load. So Q1 is the sensible heat load due to pre-cooling from the ambient temperature to a lower temperature which is above freezing. Then sensible heat load above freezing, Q2. Here Q2 is nothing but Q1 in the positive temperature. And for pre-cooling, it is from T1 to T2, then from T2 to freezing, then freezing process, that is latent heat, then from freezing to the final temperature. So it is T1 to T2, T2 to TF, TF to T3. So let me, this one. The process is like this. First is T1 to T2, initial temperature, temperature of product. This is temperature after pre-cooling. Then from T2 to TF, that is sensible. This process is sensible heat above freezing, and from TF to T3. So from T1 to T2, that is heat removal due to pre-cooling. Then from T2 to TF, that is sensible heat. Then we have got at this point latent heat. Latent heat. Then from TF to T3, it is sensible heat below freezing. It's from T1 to T2, then from T2 to TF, then the latent heat load, then from TF to T3. So there are four temperatures here. Whereas in case of positive temperature application, it is only 3 temperatures. I will be designing 2 cold storages depending upon the time availability, maybe one in part 1 and another one in part 2, pertaining to the negative temperature application. And one more design will be carried out in the next lecture, that is lecture number 26. Design a cold storage for freezing assorted fish in a blast freezer. Assorted fish in a blast freezer. So the product is fish in a blast freezer for the following conditions. Blast freezer, the cooling process is achieved by high velocity air, high velocity cold air. There is one more freezer that is called plate freezer. The second design in this part 1 of the lecture is I will be designing the cold storage for a plate freezer. The difference between blast freezer and plate freezer is in plate freezer, the cold plate will be in direct contact with the product for achieving cooling process, whereas in a blast freezer, cold air with high velocity will be circulated. So the dimensions of the room are given. Ambient condition is given. Blast freezer room temperature is given -35. Quantity to be frozen per batch is 1 ton. Product temperature below freezing is -10. Product temperature above freezing is +10. So it is from 10 to, I think, yes, above freezing is 10, below freezing is -10. Compressor running time is 18 hours per day. Specific capacity above freezing, specific capacity below freezing. Freezing temperature is given. Insulation is extruded polystyrene. For the previous problem, we have used expanded polystyrene. Thickness of the insulation is 200 mm. Number of fans, safety factor are given. So let us solve this problem. Question number 1. Because there are 2 designs in this lecture. Given data. Product is assorted fish. Type of freezer is blast freezer. blast freezer, insulation is extruded polystyrene, extruded polystyrene. We can use this also as EPS. When we differentiate, it's better to write whether it's extruded or expanded. Insulation thickness is given. Okay, let me write it here. I think it is given as 200 millimeter. Insulation thickness 200 millimeter. Quantity is given as 110. So that also we'll write. So number of batches is not given. So we will assume the quantity as 110 which per batch. 200 millimeter, which is equal to 0.2 meter. Mass is equal to 1 ton, which is equal to 1000 kg. So the latent heat is also given 271 H latent is equal to 271 kilojoule per kg. So let us take the other data as when we are substituting the values. There are two CP values are given. Let me write that one. Above freezing is 3.78. Below freezing is 2.14. CP value is equal to 3.78 kilojoule per kg Kelvin. This is above freezing. And CP value is equal to 2.14 kilojoule per kg Kelvin. This is below freezing. T2 is equal to 10 degrees centigrade. T3 is equal to T3 is equal to minus 10 degrees centigrade. And freezing temperature is, you look at the given data, product temperature above freezing 10 degrees centigrade, product temperature below freezing minus 10, and freezing point is given. Freezing temperature is minus 2.2. This is TF. This is TF minus 2.2. So we are the T1 value is not given, the initial temperature or the temperature. So we assume the product temperature T2, which is the temperature after pre-cooling. So let us calculate the transmission load. First one is transmission load. QT from ISHRE cold storage design guidebook. Cold storage design guidebook, table 2.1. The given insulation material is extruded polystyrene. For extruded polystyrene, K value is equal to, so let us go to table number 2.1. So this is table 2.1. This is the SI units, SI unit. This is in watt per meter Kelvin. So polystyrene extruded is in third row, expanded is in the fourth row. Corresponding to this one, the value is 0.035. K value is 0.035. 0.035 watt per meter Kelvin. If it is expanded, K value is 0.037. Now we can calculate the transmission load. QT is equal to U into A into delta T. U is equal to K by X into A is 2 into length into width plus width into height plus length into height into delta T. Let us write the dimensions of the room also in the given data. Dimensions of the room are given as length is 7.6, width is 3.7 and height is 2.4. 7.6, 3.7 and 2.4. Room dimensions. .6 meter length, width is equal to, let me check it, 7.6, 3.7 and 2.4. 3.7 meter and height is equal to 2.4 meter. So substitute the values. K value we have taken from the table. So this is the K value. Let me substitute the value. 0.035 divided by thickness of insulation is given in the problem. 200 millimeter, which is equal to 0.2 meter. 2 into the length is 7.6. 7.6 into 3.7 plus 3.7 into 2.4 plus 7.6 into 2.4 multiplied by the delta T. That is the outside temperature. Delta T is 40 minus of minus 35. If you see the outside condition, ambient condition is 40, outside temperature is this one, and the blast freezer room temperature is minus 35. That is the cold room temperature. So let me write that also in the given data. Outside temperature is equal to 40 degrees centigrade. Inside temperature, that is blast room, blast freezer room. Temperature is equal to minus 35 degrees centigrade. So this becomes the delta T. This is the delta T. So this is 40 minus of minus 35. So the transmission load comes to 1.5 kilowatt. 1.5 kilowatt. Next, let us calculate the product load. Product load. So let us calculate Q1. So when it comes to the product load, sensible heat above freezing, since we don't know the initial temperature of the product from which the product is pre-cooled, so Q1, instead of Q1, we will be having Q2. So here I am taking let me take this one. Q1 is not known, so let us take this as Q2. Let us take this as Q2, otherwise this will be confusing. So let this be Q2. Because Q1 is from temperature T1 to T2. Q2 is T2 to TF. Then latent heat, that will be taken as Q3. Latent heat is taken as Q3. And the sensible heat below freezing is taken as Q4. So this will be Q1 is equal to, since if it is not given, you will take 0. So this will be Q1 plus Q2 plus Q3 plus Q4. Q5 we will take it as respiration. So now it is clear. Q1, Q2, Q3, Q4, Q5. So here it will be Q5. Let us come to this Q2. So the reason why I am not calculating Q1 is from the initial temperature to the pre-cooling temperature, it is not given. we assume the given temperature 10 degree as the after pre-cooling temperature. So let me change the pen color. Cooling from 10 to minus 2.2. Sensible heat above freezing. That is cooling from 10 degree centigrade. Let us write the 10 degree is T2 to TF minus 2 minus 2.2 degree centigrade. So this will be Q2 is equal to, I am using the notations which I explained in the first slide. This is the first slide. Q1 sensible heat due to pre-cooling, that is from T1 to T2. But now we are calculating sensible heat above freezing. So it will be Q2, Q3, Q4, and there will be one more Q5. Q5 will be the respiration load. That will be the respiration load. So let me add this also. Q5 will be, it will be respiration load. Of course, it is 0 for dead products, respiration. Let me add this also. So since this T1 is unknown, we are not able to find out Q1. So let us assume that it is 0. And I am finding Q2 above freezing. So we have to substitute the CP value above freezing. So Q2 is equal to MCP delta T. Delta T is from, this is T2, 10 degree centigrade is T2. The cooling is from T2 to TF. So 10 minus of minus 2.2. So this is T2 minus TF. I am using the same formula which I have explained at the beginning of this lecture. So 1 ton is 1000 kg. CP is 3.78. 3.78. That is, it is given above freezing. CP value above freezing is 3.78. T2 is 10. 10 minus of freezing temperature is minus 2.2. So when we calculate, we get Q2 is equal to 12.8 kilowatt. So you will get it in kilojoules. Divided by 3600. 46116 kilojoule, which is equal to 46116 divided by 3600 will give in kilojoules per second. So which is equal to 12.8 kilowatt. 12.8 kilowatt. So this is Q2. Now latent heat is Q3. That is M into H of latent. That is 1000 into, latent heat is given in the question, 271 kilojoule per kg into 271. So that is equal to 271,000 kilojoule. So 271,000 kilojoule. When we divide this kilojoule by 3600, we will get kilojoules per second, which is kilowatts. So that is equal to 271,000 divided by 3600, that is kilojoules per second, which is equal to 75.3 kilowatts. .3 kilowatts. Next, let us calculate Q4. Q4 is sensible heat below freezing. This is above freezing. This is Q2 is above freezing. Q4 is sensible heat below freezing. Sensible heat below freezing. That will be Q4, that is equal to MCP delta T. Delta T is from the freezing point to the next temperature, that is T3. That is TF minus T3. If you see the formula, sensible heat below freezing is Q4 equal to T from Tf to T3. T3 is given MCP. So it is cooling from Tf to minus 2.2 to minus 10. T3 is given as minus 10. So that is cooling from minus 2.2 degrees centigrade to minus 10 degrees centigrade. So substitute the values. M is 1000. Here we have to substitute the value of Cp below freezing. Value of Cp below freezing, that is 2.14. 2.14 into Tf is minus 2.2 minus of minus 10. When we calculate, Q4 is equal to 16,692 kilojoule. 16,692 kilojoule, which is equal to 16,692 divided by 3,600. That is equal to 4.6 kilowatts. 4.6 kilowatts. 4.6 kilowatts. Respiration load, Q5 is equal to 0. Since assorted fish is not a live product, now the total product load is Qp is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. Because the pre-cooling details are not known, so it is assumed this is negligible. Q2 is calculated. Q2 is 12.8. Q3 is 75.3. Q4 is 4.6. And Q5 is 0. We get the total product load as 92.7 kilowatt. So next, equipment load. Since we have already calculated, I will quickly go through it. From ISHRE Cold Storage Design Handbook, table 2.12, corresponding to 2.2 kilowatt, because this is given. This details is given in the question. Number of fans are 3 of each 2.2 kilowatt. So now the equipment load is, third one is equipment load. That is QF. So QF is equal to number of fans into connected load in refrigerated space. So this has to be taken from the table. So from ISHRE Cold Storage Design Guidebook, for the given power rating is 2.2 kilowatt. 2.2 kilowatt. So if you see the table, so this is motor kilowatt. Motor kilowatt. 2.2 is here. And this column only we have to use. The connected refrigeration load is 2763. 2763 watts for 2.2 kilowatt motor power for 2.2 kilowatt. The connected load in refrigerated spaces let us check the value once again. 2763 watts. 2763 watts. Therefore, substitute this value here. QF is equal to number of fans is 3 into 2763. This comes to around 8 kilowatts. This comes to around 8.3 kilowatt. 8.3 kilowatt. Total load is summation of transmission load, product load and fan load. The other loads are not there, are not there. According to the data given, we have calculated the loads. So total load is equal to, for this case, total load is equal to, Q is equal to transmission load plus product load plus equipment load. So this is, transmission load is 1.5 kilowatt, 1.5 kilowatt. Product load is 92.7 kilowatt. And fan load is 8.3 kilowatt. 8.3 kilowatt. So Q is equal to, the total load comes to 102.5 kilowatt. 102.5 kilowatt. Considering safety factor of 10%, it is given in the question, or even if it is, therefore Q is equal to 102.5 into 1.1. So this is equal to 112.7 kilowatt. 112.7 kilowatt. And the compressor running hour is given. So it is given as the compressor runs for 18 hours per day. All these data are given in the question. If you look at the data, compressor running hours, compressor running time is given as 18 hours per day. So the total refrigeration load comes to, so this is equal to, let me show this calculation. So for compressor running hours, the total refrigeration load is 150 kilowatts. 150 kilowatts. So I will stop this lecture at this point. Thank you.